chemistry can be used to accurately predict and visualize the electronic and spatial structures of a multitude of molecules, as well as modeling the reactions between them. Three-part experiment, it will be used to plot potential energy curves and find dissociation energies for diatomic molecules, as well as exploring the molecular orbitals of molecules and graphically representing hydrogenic orbitals, radial functions, and probability graphs. Potential energy graphs and find dissociation energies of diatomic molecules. The Hartree-Fock method of calculation is preferred, using a minimal basis set of STO3G, as we are dealing with relatively simple molecules, and this can be used to optimize the molecular geometry at minimum energy structures. It is important to note that when using Hartree-Fock, the total number of calculations is actually half of the spin orbitals in the molecule, as when the two atoms are not dissociated, the alpha spin orbitals are identical to the beta spin orbitals, so there is no need to calculate them separately. Once we have found the final single point energies at the increasing internuclear distances selected, we can use Avogadro to calculate the equilibrium distance at this optimized geometry. For the diatomic molecules, hydrogen bromide, hydrogen chloride, and hydrogen fluoride, we use restricted Hartree-Fock calculations until the distance between the atoms becomes so great that it passes the equilibrium distance. At this point, the bond is broken and the atoms are dissociated. We now use an unrestricted Hartree-Fock calculation, as the alpha and beta spin orbitals are calculated separately, and the hydrogen and the halogen have now an odd number of electrons, whereas they would have had an even number when combined. Mulliken partitioning is a concept based on the partial atomic charges due to the linear combinations of atomic orbitals. Effectively, Mulliken charges describe the electron density between the diatomic molecule. You would assume as the bond breaks that the electronegative atom would take most of the electrons, if not all. When studying the electron charges, we did not see this. In fact, what we saw was that some of the electron density was deposited onto the hydrogen. Theoretically, this should not happen, and also, when we change the halogen between bromine, chlorine, and fluorine, the number for the electron charge on the halogen stayed exactly the same. Therefore, we rejected this hypothesis. On this slide, you can see a graph of the increasing internuclear distances compared to the electron volt energy of the diatomic molecules. The patterns in this graph show here, where the energy for hydrogen bromide and hydrogen chloride starts to increase at 1.6 angstroms. This is because the distances for these molecules are 1.412 angstroms and 1.313 angstroms respectively between the two nuclei. Hydrogen fluoride, however, has a slightly higher point of change. It is at this point with hydrogen fluoride where the bond breaks. This is because hydrogen bromide and hydrogen chloride contain bromine and chlorine, obviously, which have a higher number of electrons. This means there is more shielding of the nuclear attraction to the hydrogen and it is easier to break the bond or remove electrons, whereas fluorine with its 9 electrons is more strongly attracted to the hydrogen, and vice versa. On this slide, due to a breakdown in communication between myself and the computer, all the data collected is actually in Hartrees, not electron volts. But the principle remains the same, and the patterns can be clearly seen in the graphs below. The dissociation energies were calculated by subtracting the energy at the point just before the equilibrium distance away from the energy at 3 angstroms. This would give the minimum energy or the dissociation energy. Hydrogen bromide and hydrogen chloride give a similar graph which correlates to their point of dissociation. Hydrogen chloride, however, is at a higher energy, as there is only 17 electrons shielding the nucleus compared to bromine's 35. Hydrogen fluoride looks completely different to the other two, and as you can see, past the point of equilibrium increases greatly with energy. As the hydrogen and the fluorine pull apart, the energy decreases as the attraction decreases. When they finally break apart, due to the electronegativity of fluorine and the initial strength of the hydrogen-fluorine bond, there is a great increase in energy as fluorine becomes incredibly reactive again. The second part of this experiment, we once again use the Hartree-Fock method of calculation, but this time for calculating the geometry of diatomic molecules in the second period. We once again use the STO3G minimal basis set, but this time we may have to alter some charges and multiplicities. We were then able to represent the molecular orbitals through VMD and find which orbitals corresponded to some of the orbitals shown below in the molecular orbital diagram. Drawn here are the molecular orbitals 2 through 6. Going from left to right, we have the 2s sigma g orbital, which is our second orbital. Our third being the 2s sigma u starred, fourth being our 2p pi u, and our fifth also being a 2p pi u orbital, as this can hold 4 electrons. And finally our 2p sigma g, in which carbon doesn't actually have any electrons, where nitrogen does. Moving on to fluorine. Orbitals 3, 4, 5 and 6, still the same orbitals as the previous slide. However, this is where things start to get interesting. The orbital mixing affects the filling of the sigma g and the pi u orbitals at this point, and that is because the increased positive charge of the nucleus causes the sigma g to be pulled to a lower energy after nitrogen in the period. So for orbital 6, it still remains a sigma g starred orbital, however it is lower in energy than the 2p pi u orbital, and you can see this in our molecular orbital diagram here. And as you can see, orbitals 7 and 8 are the 2p pi g starred orbitals, and these can withhold 4 electrons. So for oxygen, we have 16 electrons in an O2 molecule. This leaves us with 2 unpaired electrons in our pi g starred orbital. You can see these 2 orbitals here, and as both of these electrons are represented as spin up, when we are writing the code for this particular part, we must include a multiplicity of 3 for O2. Now what this means is, when we are given our output, we're actually given a group for spin up orbitals and spin down orbitals. Now including the 1s orbital, we can see we have 1, 2, 3, 4, 5, 6 spin down, and here we have 1, 2, 3, 4, 5, 6 with the 1s. Again, including the 1s, we have 1, 2, 3, 4, 5, 6, 7, 8 spin up, so it separates it out into these 2 separate groups of electrons. Our carbon, nitrogen and fluorine bond lengths were stated previously, and they are carbon-carbon is 1.233 angstroms, nitrogen is 1.1347 angstroms, and fluorine is 1.351, so they're all around the same kind of area. O2 is lower than all of these at 1.222 angstroms, but it'll be interesting to see what happens when we involve charges. The oxygen 2+. The first thing to mention is that in our output, we can see that the electrons are all paired once again, and the occupancy in each orbital is 2, as the 2+ positive charge means that it must have lost 2 electrons. Now this occurs on a previous slide as well, and this is when I was talking about the interesting things that start to happen. After nitrogen, our sigma g orbitals are pulled to a lower energy due to the increase in positive charge of the nucleus. This means that after the sigma u starred orbital, the next orbital to fill is actually the sigma g 2p here. Then we go on to fill the pi u 2p orbitals, and finally the pi g starred 2p orbitals. You can see again in the molecular orbital diagram that it is pulled to a lower level here, and this is because sigma orbitals have typically more s than p character, whereas pi orbitals are more p characterized and are affected less by this effect. Finally, in part 2, we looked at the O2 2- molecule. The way in which the orbitals fill remains the same, with our sigma g 2p being filled before our pi u 2p. But as we have a 2- charge, this means there are 2 extra electrons in our pi g starred orbitals. Now, just to emphasize, our sigma u starred orbital is empty and has been for all the molecules that we've looked at, as our 2 extra electrons will just come into our pi g starred orbital there. In part 3, we looked at graphically representing the radial function of hydrogenic orbitals, as well as their squares and the radial distribution functions. Firstly, we had to simplify the radial functions into equations that we could work with in the code. We do this as really the concept of an orbital is just a certain space or level where an electron could occupy. Here you can see the square of the radial functions for the 2s and 2p orbitals. Plotting the radial distribution functions. To do this, we take our previous equation, including the square, times it by 4 pi, and times it by the wave function squared. These plots show how the surrounding space differs as a function of distance from the nucleus. As our graphs are recorded in angstroms, I worked a few conversions to find where it is more probable to find an electron at a distance closer than the Bohr radius. Because of the inner peak on the 2s radial distribution function, and as a Bohr radius, as shown, is below 0.5 angstroms on our graphs. The electron has a higher probability of being close to the nucleus in the 2s radial distribution function. Just to show, this is the 1s orbital in the xy plane where z equals 0 in atomic units. This is for the hydrogen atom. Thank you very much for your time. I hope I've given you a thorough explanation on how we can use computational chemistry to study diatomic molecules and molecular orbitals.